Hi y'all, today we're going to go through a quick little how-to guide on having a titration of a weak acid with strong base. So before we start, go ahead and write down the information that's up at the top, please, where you're given the Ka and the information about the acid and base, and hit pause. So usually when we're doing these problems, we don't know that we have not reached equilibrium yet, but I'm just kind of going through this to show you what it looks like to not reach equilibrium yet and to go from there. So for this problem, we have a generic acid of HA, and the first thing that we have to do, since we have the acid and the base, is we have to basically show how they're reacting. So we could go ahead and say, okay, I've got 0.1 liters and it's 0.1 molar of my acid. I've got 0.05 liters and it's 0.1 molarity of my base. So from that, I can go ahead and get my moles. So now that I have my moles of each, I've got my moles of my acid, moles of my base. Now I go ahead and I do my stoich. And of course, I'm going to have this decrease by that amount because that's what's limiting me, right? And then over here, this started out as nothing, and that is going to go up by 0.005 moles, right? So now here I've got 0.005 moles, here I've got nothing, and here I've got 0.005 moles. Now, I do have, in this old notes, I do have where it says leftover millimoles, because you can use millimoles instead if you want, which is just molarity times volume in milliliters, but I'm just doing it as moles, of course, today. Now, from here, what I can do from here is now I have to realize what I have left over. And what I have left over is I have left over my A minus and I have my HA. Now, since I have my A minus and my HA, what I can do here is I can do Henderson-Hasselbalch because I have a buffer. I know I have a buffer because I have both my acid and my base. So now what I can do is pH is pKa plus the log of my base, which is A minus, over my acid, which is HA. So I solve for that and I can get my pH. Now, an interesting little side note here is that because my A minus and my HA are the same amount of moles, then therefore they're also going to have the same concentration, right? So if I go ahead now and I divide by my total volume of 0.15 liters, and I divide here by 0.15 liters, then I have my new molarities. Now, when I plug that in, I get log, in this case, of 1. Right? Because it's going to be the same molarity for each of these. Now, normally the molarities are not the same. This is just a happenstance because of the numbers that I made up today. But when they are the same, what's really nice is the log of 1 is actually 0. So when our HA and our A minus are the same, we end up really here with pH equals pKa, right? Now, that doesn't normally happen, so it's better to think about the Henderson-Hasselbalch as being the whole thing here and plugging in our values. And even if you plug them in and you do plus log of 1 and you get 0 there, it's fine. So your total answer here is 5.74 is your pH. Now, for those of you who might be interested in doing it the hard way, the old way we used to do it is we would do equilibrium instead of doing the Henderson-Hasselbalch, but that's just more of a pain in the neck that we really don't need to do that step. Okay, so what we just did was when you're doing a weak acid strong base, the equation that you would do basically if you are before the equivalence point. So when you're before the equivalence point, you have your HA and you have your A minus, and then you can do your Henderson-Hasselbalch. Once you get to the equivalence point, so that works all the way up until the equivalence point. Once you get to the equivalence point, now what you're going to do is, again, you need to do stoichiometry. So go ahead and find your moles, and hit pause, find your moles, and do your stoichiometry. Okay, so now at this point I can see that I've got a certain number of moles of my HA, it's 0.010, and it is a 1-to-1 ratio. This is also 0.010 because of the value that's given to me. And then what I have is my A minus goes from 0, and it's 1-to-1, so it goes up by 0.010, and I'm left with 0.010 moles. Now again, you could have used millimoles if you wanted to, but it's totally up to you. Now, of course, I need to get the concentration of my A minus, so go ahead and do that now. Now, I'm not done with the problem, but I went ahead right now and I took those moles divided by the volume, and I got my molarity. Now I can go on to my next step, because this A minus is going to influence my pH, because this A minus is now going to react with water and be in equilibrium. So let's do that on our next slide. All right, so since I have that A minus, I go ahead and I show my equilibrium reaction as reacting with water, and it makes HA and OH minus. Now I can do a whole ice table, but of course the initials are 0 for the HA and the OH minus, etc. But instead what I'm going to do is I'm just going to jump to the equilibrium values, because we're not worrying about adding or subtracting little x from our A minus. So at equilibrium, this would be, of course, excuse me, 0.050 minus x, but x is so small it doesn't matter. And this would be x, and this would be x. So from here now, what I can do is, because A minus is acting like a weak base, I can go ahead and I can set this up as Kb, because A minus is a base, equals my HA times my hydroxide over my A minus, which of course this is x times x over 0.050. But then you might be wondering, where do I get Kb from? Well, we have to remember that Kw is Ka times Kb. So Kb is Kw over Ka. Okay, so now I went ahead and I solved for my Kb using my water constant and using my Ka. Then I can go ahead and plug it in and I can solve for x. All right, so I went ahead and I solved for x, and x is 1.7 times 10 to the minus fifth, but I have to remember what x is. Yes, x is HA, but that's not what we really care about. We care about this strong base over here, this hydroxide. So now we know that this concentration is the same as our hydroxide concentration. So go ahead now and solve for POH and then pH. So pause it and solve. So we can see that from that hydroxide concentration, we solve for POH, we get 4.77, and to get pH, I know that pH plus POH is 14, so pH is 14 minus POH. So I get a pH of 9.23. Now, our last type here is we are beyond or after the equivalence point. So in this case, we're going to have extra sodium hydroxide. See if you could try to do this problem and then come back and look at what I did. So pause it and try it. Okay, so this is where I'm at so far. I go ahead and I do my stoich, and I find that since my HA is limiting me, then I'm going to go ahead and use all of that up, and I'm going to have leftover hydroxide, and I'm also going to have some A minus. Now I know that the A minus is a lot bigger than the hydroxide, but the thing here is that hydroxide is a much stronger base than any conjugate base of a weak acid that we would have. So in order to get now our pH, we're going to go ahead and use our hydroxide that's left over, get POH and then pH. So do that if you haven't done that already. Okay, so just to walk you through what I did here, I went ahead and I divided by my total volume. I got my hydroxide concentration. Then I went ahead and plugged it into my POH equation. I got 1.96. Then to get pH, I have to do pH is the 14 minus the minus the POH, 14 minus the POH. So I get my final pH of 12.04. Now notice how the pH has changed over this titration. It started out really low and it ended up really high, which makes sense because we're adding our strong base to a weak acid.